CLI and a cross-platform IDE for C and C++. Download now.
Hello everyone, welcome to my talk, Monads meet Mutexes. My name is Arne Berger, and today I want to talk to you about a framework, a library that I developed within my team that combines both of these building blocks to solve one of the common pain points I saw in our development. But before I start with the topic, some words about myself. I started using C++ professionally in 2011, and my former background is in mathematical optimization. So my professional career started with scientific computing at the university, and during my work as a scientific assistant, I had many different projects, all featuring different topics, most of them including C++, and I had a lot of mainly student co-workers that I needed to teach C++, answer the questions, bring them up to speed with coding because it was quite new to them. And through this teaching, through this getting questions all the time, I learned a lot about C++, about myself, and also about what are the pain points that keep coming up. And I like to solve these pain points with library code. Currently, I'm working for Bruker Daltonics, which is a company that does many things, but my department does mass spectrometers, so instruments where you can put in biological samples, and it tells you what's in that sample, which proteins are in there, which liquids, whatever you want to read out of it. And I'm specifically as a software lead for the so-called TIMS MRMS instrument. And if you don't know what that is, you are probably not alone. This is one of the instruments we are developing. So at the front, you see it. It's the main instrument. And then at the back, it's a very big magnet. So it's quite bigger than these MRT instruments in a clinic. It has 18 Tesla, if you want to look that up. And I'm working there in the instrument control software to make these things, this instrument scan the samples and bring the researcher the information about what's in there. But now to the topic. And I like to start my talk with a story from quite the beginning when I joined Bruker. I looked at the code we had there, and one pattern came up at several occasions, and I want to show you one example of how it looked like, because that was the motivation for me developing the library. Here you see the class core. So it's a core that is mainly responsible for scheduling our scan task. And it starts with a simple member here with a task that is currently running, might be a null pointer because nothing is running. So far, so good. And then it has other members. One of them is a mutex and a condition variable. And then it has a so-called task portal where the details doesn't matter that much. And then it has this comment here, this suspicious comment protected by a mutex. And that was first thing where I noticed, this comment might tell me something. I will come back to this, but let's first look at the functions, or some of the functions this class does or has. One of them is a run function, so the scheduling takes place, basically in an infinite loop until we cancel all the thing. And within this loop, it gets the next task, which might be a null pointer. And if we have a task, we do some preparation for the scheduling, then we move it on to the currently running, and afterwards we read the data. So the details here are not that important. This is just the loop outside that accesses the internal member that was not protected by the mutex. Let's also look at the get next task function, because there we see our mutex and our condition variable again, where we log the mutex at the beginning, and then we wait for the condition variable until our task portal has the next task, or it times out. But if it has the next task, we get it to a buffer here, And if we time out, we signal that we are still alive. So there's a reason for that. We always want to run tasks, and if we doesn't tell the firmware, here's the next task for some time, it reports an error, because usually that is an error condition. But sometimes it can take longer to prepare the task, and so we signal it, and then we move on. And then after the whole if-else case, we log the current state and return the next task, which, as I said, might be a null pointer here. And this code is perfectly fine. It works. It has worked for many years now. And it's also speaking, so you could see what it does. That is not the problem. But what I found itchy about this code all the time was the part with the members. I talked to a colleague about it and said, yeah, this pattern is somehow a code smell. This comment here tells me there is a missed encapsulation. You should put the task portal in its own class with the mutex and the condition variable and protect it, wrap it, so that you see in the type system which members are protected and which don't. And my colleague said, yeah, I see your point, but we have several locations where we have such a code, and that would somehow feel repetitive, because you would have a getter function that logs the mutex, then returns something, or a setter or something else. So it would mean all the code over and over again. And yeah, that made me think, because yeah, I saw his point. I was still, I want to encapsulate it. But I also was in a, it was in a time where I had, could think about library functions, and maybe I thought, maybe I can make up something so that we are both happy, and that will spark adoption here. And that is what turned me on my journey to create the code I will show you today. So what will we hear today? First, we are talking about, okay, what are the actual pain points in current synchronization we want to solve? There are many in synchronization. We don't solve all of them. We solve only one specific thing that I will talk again briefly. Then we will look at how do we design a wrapper class that fixes this pain point. So the API from the outside. How should it look like for the user? Then we go on, okay, what's the actual implementation? So under the hood, the thing I need to do to make the user happy. How does it impact the code? How does the code we just saw will change with that? And at the end, I will also compare to existing other approaches that do similar things or are proposed to do similar things. For that. Okay, so let's briefly recapitulate what are the pain points we want to solve. So in an abstract way, the problem is here we have a class that has a member that is not protected by a mutex and has other members that are protected. So, and I need to ensure that the problem is with comments. You don't see that in code. It is quite easy to miss locking the mutex at this point, or forget it, or lock it for the unprotected thing and maybe get a deadlock out of that. So the pain point here is, I want to encapsulate it without writing code like this, like, okay, I have one class encapsulating a thing, then another, which is semantically just another class, but has basically the same functionality. So I don't want to repeat myself. So that's the pain point I want to solve today, encapsulate the mutex and the condition variable, to make that possible. I don't want to solve all the other pain points with synchronization. There are other ways for that, and I will talk briefly about them at the end. And if there are solutions for that. Okay. Let's move on to the design of the class. How would we design a wrapper class that fixes this one problem about the encapsulation? Let's write a short to-do list for that. So what do we want? We want to encapsulate all access to the resource, to the value we are encapsulating. So the mutex should be locked every time we access it. But we want to allow modification from the outside. And we want to allow a retrieval of the resource to work with it. We want also to allow several operations under the same lock, so that we can call multiple functions without unlocking in between. And since we want to use condition variable, we need it to be combinable with other synchronization primitives. Okay, let's start. How should the basic access look like? So we define a class, synchronized resource. It's templated on the value we want to encapsulate. And then to call an arbitrary function, I called it, or I named it call protected. We're a function that we give a functor to, and then we assume, or the invariant is say, okay, it should be log the mutex, call the function, return. That's quite straightforward. The setter is also quite straightforward. We just call it set protected. It goes in there, logs the mutex, and modifies the value. And also getting a copy out of it is the same. Log the mutex, copy the thing out, and then go on. So that's the retrieval, but that's not all of the retrieval, but because sometimes, okay, we just don't want a copy. We need a reference, for example, out there. And that's why I also thought about the get locked function, where we say, okay, get locked and get an array type back that allows us access on the references via basically pointer semantics, or the arrow operator here, to access what's underneath, and it stays locked until this lock guard here goes out of scope, and it keeps the reference for itself. And then afterwards, it modified the value within the synchronized resource. That's the basic functions I thought of, also inspired by the code I looked at and talks to my colleagues. So that already solves 4 of our points. We encapsulated everything. We have modification. We can retrieve it as a copy or even as a reference for a short time. And we allow several operations under the same lock, either by the get locked function and then modifying that value, or by the call protected. But how do we combine it with other synchronization primitives? What we need to do is we need to encapsulate the waiting. And the basic thing is quite straightforward. We look at the functions that a condition variable offers, and then we pass that through. So we have a synced wait here, which will lock the mutex and then call the wait on the condition variable. And then in another thread, I can set the value, notify it, and then it will return. So we encapsulate the waiting. Okay, there are other functions, wait for, wait until, but all of that can be just encapsulated. And there was a point during my implementation of that when I thought, okay, that's all, I'm done. And if I look at my to-do list, yes, looks like I'm done. I now have a condition variable here. All is fine. But if I look back at the example I had here at the highlighted code, there's one thing that is not possible with the current API I proposed, and that is if you wait for the condition variable, you pass it the lock here in the top line of the if. Underneath it will unlock the mutex, or the lock, it will unlock the lock. Then wait, because it needs to allow modification from another thread. But then when it returns with the lock is again locked. So here in these lines where I have the comment here, the mutex is still, or is locked again. And that is currently not possible if I just encapsulate it, because, okay, I have one functor there and it returns, and then, I could return a lock, but that would somehow break the encapsulation. So we need to extend our to-do list, which is fine. We learn as we code. The next point is, okay, we want a flexible continuation after waiting. So we wait on the condition variable and then want to call continuation functions under the same lock duration. How could we achieve that? So this is the problem framed in code. We have the wait function as before here, and then we have another function, use result on the synced synchronized resource, and we want somehow to achieve that the mutex is still locked. And yeah, when I was shown this problem or realized that, my first idea was, okay, then I just provide another wrapper, wait and then, that waits and then calls the function here, which works quite well. So this just for it, it's a good wrapper. It does what it should. But then, yeah, as reality kicked in, let's say, I wanted to integrate it into the code base, and there's a problem. Okay, wait, and then it's fine. I wait until the predicate is fulfilled, and then call a function. But condition variables have other functions for waiting, and one of them is, for example, waitFor, which can also timeout, which is in the code we have. Okay, then I have, okay, I want to call it if I fulfill the predicate, I want to call the one thing, and if I'm in the timeout, I want to call another thing. But sometimes I want to always call something within the same lock duration, so I have an waitFor and then or else always here. And of course, I could use just the always and don't want the and then or else, or I just want the or else or not the and then. And of course, I could somehow do that with optional parameters and things, but calling code then really doesn't really look that nice. And I have the wait until and then, and just the code for it, the API of the class would blow up, and with functions that do basically the same, but over and over repeated again. And at some point, I thought, maybe I need another way to do these continuations. And then I looked at what we already had. And yeah, with new C++ standards, there were things added to, for example, the optional that are also continuation functions. So for example, here, if you have an optional from the STL, you can say, okay, it's an optional value, it's there or not. And I want to call a function if it's not there. So I call the or else and then replace it with something in there. Then I call the toIn that's just there, is just only called if the value exists. And at the end, I call value or that gives me the none string back if it wasn't convertible at all. The example might not be that realistic and good. It's inspired by what is at CPP reference, but it shows what we can do with this. So we have the optional, we have another type in the STL that is expected, that is not only if it's there or not, but it has the expected return type, or an error case, an unexpected. So it can have in the second case also a complete class or complete type that you can modify. And if you look at presentations about them, they are called monads. I don't want to go that much into detail about theory of monads. Monads were more my inspiration here. I looked a bit about the theory later on, but my inspiration were more the continuation functions. Yeah. So if you are really a monad expert and spot something in my code where you say, yeah, that looks like a monad but isn't, remember that for the Q&A later or for GatherTown. I would like to talk about it, but for this talk, remember I just interested, it was the inspiration here for the continuation functions. Okay, so with monads, what can we do? How should our API look like then? For the wait, and then, yeah, we can just say, okay, we want to call a wait that returns something. And on this something, we can then call the andThen function if we want to. And then that function is called afterwards. And for the waitFor, it would look almost the same. We call the waitFor. Then on the return thing, we call an andThen. And on that return thing, we call an or else. And then we call an always. So that's the same for wait until. And the cool thing here is, okay, in this order, it reads the same as the functions before, but here it's really optional. You could just reorder them, have two andThen functions, or leave some of them, not there, delete some of them. So you could really flexible compose this thing. And that, was my idea, what I wanted. So far, I wasn't there that I really got it, but we will talk about that in a bit. Then also one requirement more was that I also wanted to do this if these functions return something, calculate a value based on what's in there. I want to be able to get it out afterwards. So a return value that's more than, okay, you had a timeout or not. It should really be, reflect or get the return value out of it. In our example, that would mean from the beginning, that would mean, okay, in the get next task, we have our synchronized resource. We wait for it for a timeout or until the task portal has the next scan task. If we do not timeout, if the predicate is fulfilled, we pass that on and then say, okay, portal get next task, we'll return that. In the or else case, we do our signal, and then we have the always function here at the end that logs the current state and then returns the result. Because at the very end, we want to decide, okay, were we in a timeout or not? And if we have a value, return that. Otherwise, return a null pointer. And move on with that. Okay, so that's the design of the class. Now, the hard question about that, can we make that happen? What's the actual implementation for this? I mean, it's a fine wish list, but how do we make that work? And what do we need for this is, okay, first thing is we need to lock the mutex around all accesses to the resource. So these basic access functions, we need to implement them actually. And we will have a brief short look at them. And the second thing is, okay, we need to provide the same lock duration in the waiting operations as with a raw condition variable. So throughout this whole monadic chain, the lock needs to stay locked and afterwards need to unlock itself. Just think about this question for some time. I will come to that. If you have what solution for that you directly have in mind, because I had some in mind that all didn't work, but I will talk about that in a moment. First, let's look at the basic access functions. They are straightforward. Here, call protected, we lock a mutex, then call the function. Afterwards, it's unlocked by the destructor of the lock guard. And we do the same for set protected here. Lock, do what we want, and then return. And for get copy, we also do the same. The get locked thing, so where we return an access, is also quite straightforward. So get locked itself returns another type where it passes through the mutex and the resource value. And then that locked resource internally has the unique lock and also a reference wrapper to the resource. So it stores a reference to that thing. And then it has these access functions via the arrow operator and the star operator here to access it, to modify it, and to work with it. So far all quite straightforward, I would say. So we can check that off. The implementation was fine. Okay, then the second thing, provide the same lock duration in the waiting operations. What does it mean? So if we have our monadic chain here, as I call it, we have on the left side, we want to store something in the result. We first call the waitFor, which locks the mutex internally. Then we call the andThen, then or else, and then always. And in the comment below, you see for what duration the mutex needs to stay locked. So it needs to stay locked for the whole function chain without any break in it, and not longer than that. So these are the two invariants we need to protect here. And yeah, once again, think about it. If you have an intuitive solution to that, what you could do, the first thing to think about, okay, implement it like the other things, lock the thing, then do something in each function. Doesn't work because then we break the lock duration in between. So that didn't work. I now will show you one thing that also didn't work, which is, for me, it was a intuitive way to try it. So that's why I show you something that doesn't work, because that also motivates what I did later, because what I did is, yeah, first looks a bit weird, and the motivation for that, why I needed that, is this other thing that doesn't work. And which didn't work is the typical RAI lock holder. So a class that I return here in the waitFor at the top, where I lock the mutex, then pass it to the condition variable. And if it returns, I move the lock to another class. So I move the ownership to the locked result, and the locked result then offers functions like the andThen. So I move it down the chain, and the andThen function again returns the locked result, which gets passed on the ownership and so on. Which for me is okay, that's a typical C++ thing. I move the ownership through the classes, and then the last destructor is responsible for clearing up. The problem is that, of course, if I save a result, it will end up in the result and stay locked afterwards. So we have the lock duration that it's not broken in the middle, but we don't have the lock duration end when we want it to end. So if we do something else afterwards, it's still locked. Okay, that was the thing that didn't work. And then I thought, okay, I need something that takes the mutex, but is only there in the chain and will be destructed after that chain. So it's only there temporarily. And then that was somehow my idea. Okay, maybe temporaries. Maybe there's something about that. And lucky, good for me, there's this passes in the C++ standard. I cited here. You can look it up in the, I think that's the latest draft of the standard I could look up. The temporary objects are destroyed as the last step in evaluating the full expression that contains the point where they are created. Okay, what that means, the full expression, simply said, ends at the semicolon. That's it. So if I create somewhere here a temporary object that is created in this chain, then it will be destroyed as the last step after this expression ended. So all I need to do is find a way to create a temporary and not move that responsibility to the user. So I could, of course, say, yeah, user, please create the temporary and then do something. But I didn't want to do that. I wanted it to look like this, but still have a temporary here somewhere. My first idea was, okay, the first waitFor returns something that owns the mutex, and then the ownership is not passed on. And that waitFor is returning a temporary here, and the other functions also, until the always, that one is passed to the result. But the problem is, okay, if I do not do any continuation, if I only call the waitFor, then the first thing with the ownership still ends up in the result. So I needed something, a temporary that is created in this chain. So on the caller side here, not within some of these functions, and cannot end up in result. And at the point I was thinking about that, I also worked quite a lot in our code with source location, so the STL type source location, where you have quite often this pattern that you created as a default value to your function, because the default value to your function is created at the caller side. So it's created in the full expression of the caller. And so I ended up with this idea. I modified the waitFor function in a way that it takes an R value holder and gets assigned a temporary, so a default value that is created and then bound to that holder value. And within the function, I assign this holder the mutex, which I need to do. I cannot pass it to the constructor. That is not possible to pass in members here to the default value. But here I assign it, and then I return the synchronized result. I called it here without passing it any mutex or any lock, so it doesn't know anything about the mutex. And this holder then is extended until the end of the full expression, because the temporary thing, the default constructed thing, is constructed at the caller side. So yeah, as if I would call the function and create it on the outside, and it's bound to the R value. I need a R value reference here because I cannot take it by value, because then it's not clear if it's a temporary or if the temporary is passed to the value, and due to copy elision then there is no temporary anymore. I tried that first with pass by value. It worked with Clang and GCC, but not with MSVC. And my research was like, yeah, it's implementation defined, I think, but nevertheless, we use MSVC and it didn't work with that compiler, so couldn't use that. I also couldn't use const reference because it's not const. I need to assign it something. So I use an R value reference here, even though I never forward or move it within this function. Just bind it to a temporary. Okay, then next thing is that I have the andThen function, which works on the synchronized result and also returns a synchronized result. And it's only callable on R values here because I want to work this only within the chain. So you cannot call it on the result later. You need to call it directly. Of course, you could move the thing, but then hopefully you would spot it in code review. And what this gives us is, if I do something from the outside, it just looks like we wanted it. We have the waitFor and then the continuations. The waitFor creates this temporary lock holder without the user seeing it. So the user, it's of course exposed. If they look at the code, they will see it, but they don't need to care about it from any perspective. They just pass in what they passed in before. So it's created and then it's destroyed as the last step of the full expression here. And that finally worked with keeping up the lock duration I wanted. And if I do not do any continuation, that doesn't matter because the synchronized result doesn't know anything about any locks. So it's still only locked for the waitFor call and unlocked afterwards. So with that, I come back to my to-do list here. Both are checked off, and why I was quite happy to have this idea. It took me some time to figure that out. And at some point I told my team, I just need to figure out this one problem with the lock duration. And afterwards I'm almost done because the rest I already did with the other thing, with the basic access thing. So I only need the time to implement that. And that, of course, that wasn't the case because then we had the engineering part, the questions. Okay, what about references? What about void? And how can we test this thing? And I don't want to go into too much detail for all of these things, but I want to show some key points that influence how we work with the type and what is possible with that. And I want to also show something about how I tested it, because I also want to inspire or want to get some feedback on that, because I'm not sure if it's actually a good thing or just a clever thing that works. Okay. Sorry. Let's first talk about references. What's the problem with references? If we look at our chain, okay, the waitFor call with predicate is just fine. And then if we want to continue on that chain, we of course want a reference to our wrapped resource, because maybe we want to modify it, or do something else with it, or just don't want to copy it because it's quite big, things like that. We want a reference to that thing to be able to work with it. And we also want to be able to pass that reference on to the next thing. So if we want to compose two andThen functions after another, or have an always call there, the first thing should be able to return a reference so that the next thing can work with that. And that's okay. As long as we are still in the chain, our invariants hold, the mutex is locked, and we can work with that without fearing any race conditions. But let's just assume we at some point delete the second andThen and are in a rush and forget to modify something else. And if we return that even to an encapsulated value, we end up with a reference to our thing on the inside and can modify it after the lock duration ended. And of course, with C++, you could do that anyway. I can just save a pointer captured in the lambda to the outside world. So it's not about not making it up or making it absolutely impossible to save a reference. I think that's not possible. It's C++. You can always get somehow access to it. But I want to make it hard and mainly not possible by accident. And with this, as I said, you can just delete the second thing and you would end up with a reference. Might be a problem. So I wanted to prevent that. And the idea about that was, okay, my class, the thing that is passed on through the chain, has an internal value, which reflects, or starts with the type we have in the wrapper class in the synchronized resource. So a reference to it. But it also defines a return type from that. And that is that type without a reference and without const volatile. So just remove cvref. If you're not familiar with this template thing, that removes the reference out of it. So I get the right type, but not a reference. And then it provides access functions on the outside. Here, a simple get function that gives me an expected, here an TL expected, what we used internally. Could also be a std expected. That returns an expected of this return type, which is then no reference at all. And I also have other access functions at the end, a value or. So the expected has the non-timeout type and the timeout type, so that you can distinguish in which thing you are. If you say, okay, I want the value from the non-timeout pass or the other thing, that you can call value or also get the return type without the reference. Or you have the unwrap function that checks if both paths have the same type in it after all the whole chain, and then just give you the value for that that is active. But still, it only gives you a copy. That then requires the user to call this get function at the end to get a user can work with. There were other ways first without this call so that they could directly work with it. But I think one function more, okay, sometimes people talk a lot about too many symbols, but one function call more is better than an accidental leakage of references here. So I just wanted it to find the problems at compile time. And if you forget that, you get a compile error. Okay, compile again, fix it. That's better than a bug due to a reference. So that's the thing with references. The next thing, okay, what about void? There we need first to talk about what's the problem with void. One problem with it is if we look at this get function here, for example, with the expected, that has the value of the path of the andThen. So if the andThen returns something, it has that value in it. And on the other side, it has the path from the timeout. So if the or else returns something, it has that in it. In our example from the beginning, the timeout case just signaled something and didn't return something. So it returned a void, basically. And that is for us still meaningful because we still know, okay, we are on this timeout path. But for example, an expected cannot work with that. An expected cannot have a void on the error case, so on the unexpected case. So we needed to treat that. There are, of course, more problems with void, like, okay, what to do if you then have the void and the next function is called, you cannot pass in parameters, so template metaprogramming problems that are solved. But here also this expected, which we also used as internal storage. And the solution to that was somehow easy. You see here in this very long chain in the middle that I say, okay, if it's void, then I do not use a void thing, but I use some class, a synchronized error class to signal, okay, here was a timeout, and that represents the void. That uses up some extra bits, but at the places we are using this code, we don't care about these few extra bits. They don't matter compared to other things. So that's how I treated void, or at least some of the problems you got with void. Void really, for the template things, was one of the bigger problems to figure out. Okay. With that, we are through our list for the engineering so far. Only testing it is left. Testing libraries for asynchronous things is quite hard, I find, because usually I try to write unit tests from the outside view. So I want to describe in the unit test the observable behavior of something, but with asynchronous code, parallel code, the behavior is not the same for every execution. That's one of the problems we need to solve. So you really have to design something. Okay, here I want to run this, and then I make a barrier here, and I don't want to execute this code behind that before I had that, and thresholds and things like that. I did this thing. I did some unit tests that hopefully test what they should. But for one point in this wrapper class, I wanted to test an internal thing, and that is for the lock duration. So that's one of the key invariants here. It's also one of the things that during development I messed up with the first few things that didn't work. And so I wanted to find a way to test, okay, is the mutex currently locked or not? So usually I try to not test internal things like that, or did the class call the internal member? But here that is really the point of the whole class. So I wanted to test it. And as I said, this whole thing, feedback is welcome. I like the thing I work on, but let's first move through it, and then you can state your opinion on that later. So I wanted to make it possible to say if a mutex was used is locked or not, but I didn't want to pass in an instance of that mutex through the constructor. So I made a template argument out of it that you can change what mutex is used. That might even be useful at some point for a user. And then I designed a test mutex that has a static member locked, which is set to true on the lock call and set to false on the unlock call. And since it's static and public, I can access it without having access to an instance. So I can just call it via the type name. And that put like this. I define my test case here, my resource at the beginning, and I templatize it for the test mutex. And then I expect it to be false at the beginning and expect it to be locked within the chain, and then expect it to be false at the end again. So that would be my test case here. The problem with this is if you copy paste it to another test, you cannot run it in parallel because two test muteces share the same variable. And we want to be able to run our tests in parallel, to save time and things like that. So they shouldn't be coupled in that way. So I needed to find a way to modify that. And one idea I had is if I go back here to my test mutex class, to give it a tag, so type name tag. That's can be a trick with template beta programming or with template programming, that now every if I have a test mutex of int, for example, and a test mutex of double, they do not have the same locked variable. So the test mutex of int has one and the test mutex of double has one, and if I access them, they are different things. But I needed a way to define unique tags that you couldn't mess up. So of course you can pass in a struct that is basically called like the test case you are currently running. Then you would have a nice way of creating simple names. The problem with that is if you copy and paste the first line of your test where you create your resource and forget the renaming, then you end up still with the same time. And I wanted something where I say, okay, if I copy this type to the next case, test case, it just directly gets a new type. And here's where my trick came in, and that is that I used the type of a lambda expression as the tag here. And that's really where I would like to hear some feedback about. Because the lambda expression, the type, if you go, for example, to CPP inside, you see that the type is based on the line it's in. So if I do the same thing on the next line, it's a different type. And if I then do a using on that and define that as my tag or as my mutex here, I can copy the first two lines here to the next test case, and they are different types then. And then I can check it, run it in parallel, and work with that. And that worked. So far I haven't had problems with that, and I find it quite nice. Quite good thing. So I wanted it to share. I want to get some discussions on that. Okay, so that's our implementation. We have tested it, we have done the engineering part, we have thought about it. Now let's bring it to the user. We already saw some of the examples here, how it changes things, but let's go back to the example from the beginning. So if we have our class core again here and say, okay, we have the currently running task and the other members, that was the before thing. If we now exchange this with our synchronized resource, then we have two members. One is just a simple member, and the other one is a synchronized resource that says in the type that it has a mutex in it and a condition variable if you want to look that up. Otherwise, it just exposes an API that you can use and makes errors much harder than before. And this is a function from before we had at the beginning with the if, wait for, and then next task thing. And that now looks like this. We saw this before with a function chain from the top. So we have the wait for, then we have the andThen, or else, and always, that signal lock. And then we have the value or function that returns the null pointer or the value from the, or the next task, basically. So clear way down, you can read it, and you don't have to care about anything from mutex, condition variable, things like that. You cannot, or it's quite hard to mess that up. Okay, last but not least, when I presented the first version of my wrapper class, after some time, a colleague came to me and said, yeah, did you have a look at this proposal here? It looks like it wants to do the same. So Now I'm doing that. I'm looking at, okay, are there things out there that try to achieve the same? And yes, there are. There is currently a proposal that is not new. It's already there for quite some time. Here's a link to the current draft of that proposal, and it's called synchronized value. So quite the same in the name. And that one proposes, at least the last paper from that proposes a single apply function to achieve everything. So you have the same thing here. You can template, give it a template parameter on the type it should wrap. And then if you want to read it, for example, you call an apply with the synchronized value and the function you want to apply it to. So that's similar to tuples, where you also have apply function. And then you can, of course, return it or set it. You do that with the same apply function. So that's basically everything it does. It wraps it and has an apply function. What you can do is pass in multiple of these synchronized value to the same apply function and then work on them the same, and they will, under the hood, execute some deadlock preventing algorithm to lock them all together without causing deadlocks to them, that you could do with this apply. Okay, let's compare that with what I have done. So on the left side, the synchronized value has a single access, the apply function, while the synchronized resource has several access functions: get call protected, get lock, set lock, get copy. Call protected is somehow the same as the apply, or you can achieve somehow the same with it. So you could just get away with call protected. As I said, I was made aware of this after I was somehow through the basic things of the thing. When I think about it, the single apply for it, I find it quite nice. It's so simple that makes it nice. So yeah, maybe I would even go back to just use the call protected. Of course, as far as I could see, the synchronized value supports only mutex wrapping, but I could have missed something there. While my type is designed to also include condition variable and monadic continuations. Of course, they are only needed because of the condition variable. One thing the synchronized value can do is lock multiple things together with a deadlock prevention scheme that I don't have. I have only one wrapper per value. Main reason for that is that we do not have a lot use cases for two muteces or two different protected things and then be locked together. We mainly have, okay, we lock this one thing to communicate. And so there wasn't a need to develop that. So that's the main reason. So that was one thing I wanted to compare with. The other one was, and that was I came mainly to during the preparation of this talk, is expected, because I have the synchronized resource as a wrapper type, but I also have the synchronized results that is then passed on through the monadic chain. And during preparation or even during writing the code, I noticed it's somehow similar to the expected type. It has two states that you can work on and do things. So I thought, can I replace it? And here's a comparison for that. So an expected has an expected versus an unexpected value, while I have a no timeout case versus a timeout case, but that's just the words, not even implementation. You could just replace it. The expected also has monadic functions, and then or else, and transform error, where I have and then or else and always. Of course, with the naming, it's a bit broken because my and then or else is the transform error from the expected. And in the and then or else function there, you could return an expected itself, where I first didn't see the reason why they did it that way. After listening to some podcast, I learned, okay, it's because then you can change the path you're on. You can go from the and then path to the unexpected and so on. I didn't see that, so I designed it my way with the transform error that just take a value, return a value, and they are created in the respective parts. One thing I have is also the always function that is, of course, not needed for an expected, because you can just do it after the continuation, because you have to probably do the if case there anyway. I need it to make it possible to call it in the chain under the lock duration. So that's something I needed. Expected also can do no void in the unexpected case and cannot handle references on its own. Okay, you could solve that by putting the wrapper class in the expected, but also the synchronized result only works on R values, and that's something quite important, that you can only call them easily within the chain, and otherwise you have to do some moves and then where I hope that's fine during a code review at least. I didn't see so far something escaping someone doing that. So that's something, that for me somehow doesn't make it possible to use expected in an easy way directly as a replacement for the synchronized result. Okay. And as promised, a short word about other ways for synchronization. So I was only talking about one pain point with muteces. So unstructured synchronization. There are a lot of other ways that are, in most cases, better than using raw muteces. So you could use std_async to just get a task. You can use libraries for tasks, for thread pools, task worker, task queues, things like that. You have the sender and receiver pattern with C++26. I had a detailed look at that, but it also achieves quite a lot of that. So there are a lot of ways to use other synchronization patterns, which are better in the way that they solve a lot of pain points, and then you don't even have the problem I proposed here. Mine is for mainly the motivation was, okay, I have code that is already with unstructured muteces, and you would need a lot of refactoring to use these other patterns. And then it's easy for a team to adopt my wrapper instead of refactoring, which will solve at least some of the problems. And to get to all the other things, I recently watched the talk you see here, C++ parallel programming models, which was a nice overview about all these patterns. So don't forget that just because I have a wrapper doesn't mean always use that wrapper. And for the conclusion at the end, I want to say something. Okay, I have two classes here, the synchronized result and the synchronized resource, and both of them together are what I propose. And at the beginning, I was saying, okay, I don't know if it's really a monad or if it just looks like one. But what I find mainly is, okay, the synchronized result is the monad, and the synchronized resource is the wrapper around the mutex. And that's why monads meet muteces in my library class. And that's also the final word about the topic. If you want to discuss this topic with me, if you want to discuss if it's really a monad, or if you saw a problem in my library, I would really like to hear about that problem, because we are using it in production code and I want to hear about the problem. Please go to the Q&A afterwards in GatherTown, or speak to me in GatherTown in the next days. If I'm in GatherTown, I'm very happy to talk to people. So just stop by, say, hey, Arne, I watched your talk, I saw this. If you're watching this on YouTube later, please leave a comment. I will read them, try to answer them. You can also leave me a message in the Discord, of course, of this conference. And if you want to contact me privately, best way is LinkedIn, here, my profile. You can send me a message. I'm happy to discuss coding things with you. And with that, I'm done. Thank you all for your attention, and we hopefully see each other in GatherTown in a minute.